There we go. All right, so my name's Evan. My pronouns are he and him. And it's my first time in Monitorama. It's been a lot of fun. It's been a blast, just getting to know all of you. This is a really, really good place. And today I'm going to talk to you about histograms. Who's excited? I'm the lead for an open source project called PhyloDB. This is a distributed Prometheus. But I am here to talk to you about, this is my dog, Indy, by the way. So I'm here to talk to you about, so why do we need histograms? I think this probably needs no introduction, but it's not really practical for most folks to be tracking every single request and sending that to their data, right? If I have a web service that simply services, 2,000 requests a second, right? So I'm sending 2,000 data points. That's not really feasible. So what we do is that we quantize and count these measurements, and then we say, this is a distribution. And this lets us do some interesting things. So let's look at the evolution of histograms a little bit, right? Everyone loves history. So in the beginning, well, actually not the beginning, but this is because this is still done today by a lot of client libraries, right? What we do is that the client library will say, okay, let me collect all these measurements, and let me pre-aggregate some stuff. So I'm going to send the P50, P90, P99 to some backend, and this works with just about anything. It goes into a bunch of standard boxes. This is good, so I can get some measurements, but there are some issues with that, right? Like, you pre-aggregate, you can't really get. You can't do anything other than what you send. And you have some problems with aggregating. So then we evolved to having histograms with buckets, for example, like Prometheus histograms. And now, more recently, we're able to do more with these things. They go into a lot more modern stacks. I mean, actually, Prometheus has only been around for a couple years. So this workflow, end-to-end, is actually not, is actually still relatively new. And there are other kinds of things that have been developed at the client end, but are sort of really not, there's some really neat stuff. These are just HDR histograms, kind of at the more bleeding edge. Really, really good libraries. On the other hand, they are, it's kind of like we don't really know what to do with them. Yeah, right. But let's start with pictures. Everyone loves pictures. This gets pretty excited. So what we have here is that we have three different quantiles, or percentages. Right, I have some latency number I want to track. I want to see, like, how is this going to meet some SLA? So here we have the P50, P90, and I think this is a 99%. Yeah, but I kind of clipped off the legend by accident. So this is good for SLA compliance. You kind of see, okay, where are things? Okay, that's good. Now, let's see what happens when we have, oh, and by the way, this is actually an aggregate. So first thing that you want to note is this looks really nice, but actually to even get to this point and graph it in Grafana, I actually have to have histograms that are aggregatable, right? Because this might come from, say, 100 nodes. And so I have to actually aggregate this data from 100 nodes to even get at these percentiles. Now, the next observation is, let's say that I have an incident. Now, what happened to that pretty graph that I had, right? All of a sudden, the only thing that I see here is this 99 percentile line. It's kind of doing a lot of spikes. And normally what was in the range of like, say 100 milliseconds, it suddenly has spiked up. So something has clearly happened. So this kind of graph will tell you when things happened. Unfortunately, it doesn't really tell me much more than that because the distribution has completely disappeared. It's kind of gone squashed. So let's see if we can do a little better, right? So let's use some heat maps. Now, this is really, really nice. These are Grafana heat maps. And what I have on the left-hand side are bucket values, basically levels or thresholds, right? And on the time on the x-axis. And this tells me several things that I could not tell with the previous display. First of all, I can see at a single glance that there's a periodic load. This is very obvious, which was not obvious from the previous graph. This is, by the way, the same incident. And I can also see very easily where the latency quantiles are. I can see where most of the latency is concentrated at the 5 to 10 millisecond range most of the time. And then I can see that at 1530, that clearly something happened. But I can see now very clearly that most of the latency actually did not go up that much. It went into the next tier, kind of like that 10 to 25 millisecond range. But there's a whole bunch of noise up there in the upper end. That is kind of masking this about, say, 2 to 3x average increase with a lot more noise. And so this can help you pinpoint or get a much better understanding of what's going on, right? By the way, just a really quick note on Grafana heat maps, that there are two options, okay, for the data format. There is a time series and a time series bucket. The easiest thing to do is to pick time series because Grafana will just pull your raw data, but that only scales so far, you know, like about I mean, I don't have exact numbers, but above a certain range, you're going to start bogging down either, you know, your TSDB or something else. So I recommend doing buckets because that only pulls in as many time series as you have buckets. So from the previous examples, like we like these rich visualizations. There are different purposes for each one. We can arrive at a notion of what do we consider a useful histogram. So let's go over these properties. I think these are important. The first one is that histograms need to be aggregatable. If you have percentiles, for example, percentiles aren't aggregatable. If you have, from each node, you have a P50, you know, P99, how do you combine that? I mean, you can kind of fudge it a little bit. You can average, but those don't really give you good answers. The second one is that we want to support a variety of different functions, right? So the more kinds of queries and visualizations you can derive from a histogram, the more useful it is. So it is good to get percentiles and rank, but you might want some other things like that. So let me just take a quick survey here. Everyone loves surveys. First of all, how many folks are using histograms in a monitoring tool? That's not as many hands I would think, right? And okay, so out of those, how many folks are using it for percentiles or rank or quantiles? And how many folks have played around with the other, for example, Prometheus functions, such as comparing thresholds, let's say how many requests I have under 300 milliseconds, or you know, like things other than quantiles? Few hands. All right, thank you. So we might want to support heat maps over time, right? Another property is that you should have some notion of how accurate it is. You should be able to control how accurate it is. And we'll get into that in 1 second. Finally, we want histograms that can scale and be efficient, meaning we ought not to be afraid of using them, right? It is a very useful tool. We want to be able to use it. And if we find them useful, we should be able to use it without fear. So let's get into one category first, which is accuracy. And by the way, these are trade-offs, right? So some of these things, accuracy, scale, are inherently trade-offs. Okay, so this is, I promise you, I really only have 2 slides with like math in it. I will make you do a calculus. So this is a really simple equation that if you have bucketed histograms, the max measurement error or quantile error for any one bucket is equal to the width of the bucket divided by its lower bound. And I won't get into the details of that, but if you're interested in that, you know, you can come talk to me afterwards. Now, I set an example for a range of values that is captured by histogram. 1,000 to 6E10 is basically, if you measure nanoseconds, a latency. This is basically measuring a latency from 1 microsecond up to 60 seconds, right? And what I did is I calculated this error percentage and number of buckets you would need to support that for 2 different maximum error percentages. So the first conclusion is don't use linear bucket configurations. They basically don't work. If you actually care about your error percentage and you want to limit it, you need like basically a completely unrealistic number to really have a nice error property, right? So use exponential buckets. Exponential buckets, or you can call it geometric, which is the same thing, is basically saying that my buckets are going to be organized like the next bucket is always a constant ratio from your previous one. And if you do that, then you get a much nicer number. For 100% max error, you have 26 buckets in this case, and for 10%, you have 188. So consistent error rates, good, because you never know exactly where, during an incident, where that thing is going to go. The third point is that and I think this is true, maybe I'll get another show of hands. How many people are using, are kind of just defining their histogram buckets in Prometheus using just using some custom methodology? I mean, sometimes you do that too, right? So it's likely if you're doing that, and most people don't like to list out like 200 buckets, right? It's likely if you're doing that, you probably have a max error percentage somewhere north of 100%. And I'm sorry if you're realizing that now. This is what I recommend, is a methodology for configuring histograms. First of all, start with what you believe is a reasonable min and max value. Then pick the maximum amount of error you're willing to tolerate. Then you can use this formula that I've come up with, which is basically you do some basic logarithm math. This is the only other formula I think I have in here. So as an example, let's say that I want my max error rate to be 50%. So what I do is I plug in the ratio of the max and the min. So you take the log of that and divide by the log of 1 plus 0.5. And this gives you an answer of how many buckets you need. Then you feed it into the API, you say exponential buckets, then you feed it in. And this is, so yeah, this is not very hard to do, and it's pretty systematic. What I'd like to spend some time talking to you, though, is about histograms at scale. So how do we solve the problem of, so now you have a way of configuring histograms. The next challenge that you face is you realize, oh, maybe I actually need a lot of buckets to achieve the kind of accuracy that I want. But you realize that you might have a scale problem. So we'd like to introduce a concept which is treating histograms as first-class citizens. And what I mean by that is that starting in the client, you have good client libraries that we want to model and we want to transport and we want to store histograms as their own entity from throughout the pipeline from front to the back. And this gives us a lot of really nice properties. Among them are that they allow us to scale really well for storage network and things like that. And because we're treating them as a single entity, we can do aggregations and take care of edge cases and take care of accuracy during edge cases. And we can also try to support better accuracy and features, and as well as adapt to future evolutions in histogram design. And this is something that I haven't heard many folks think about or talk about. So let's dive right in. If you're using Prometheus, this is how Prometheus models histograms. So first of all, you have a sum time series. This is basically the sum of all of the values that were captured during that, or is a running sum of the values captured. And then you have a count, or how many values were captured during the time. And then you have a time series for each bucket. And what happens is that you will have, this is hopefully not news for folks, but just want to make sure that we're on the same page. The Prometheus client will insert a label called the LE tag, which stands for less than equal to, right? So at LE 2.0, it means that I have, say, 2 counts that are at the value of 2 or less, right? And at LE10, that means that I have, say, 5 counts that were 10 or less that has been collected so far. And these accumulate over time as counters. So let's look at the scale problem a little bit. Let's say that I have an app which has 100 metrics. It's, nice round number. And let's say 20 of them are histograms. They measure latency or whatever it is, right? And let's say that I'm talking about the same range again. It's from 1 microsecond to 60 seconds. And let's look at how the number of histograms scales with different amounts of error that we want to tolerate. At 50%, we need 44 buckets per histogram. And even at that level, we can see that the number of time series needed for histograms is already completely dominates all of the other ones. It's about a 10-to-1 ratio, even though histograms are only 20% of the metrics. If I go to a 2% max error, I'm looking at 900 buckets, and now I have about 18,000 total series, which completely dominates the 80 regular metrics. And we can see that if we desire certain reasonable levels of permissible error, that we quickly get at a pretty big problem. So I work with an actual system that has hundreds of millions of metrics. Each of them has a histogram with 64 buckets. So using this kind of data model would lead to tens of billions of time series. And we wanted to find a better solution to this problem. The other issue that we find is that you will find that the raw data that's being sent over the wire, because histograms are represented as separate time series for each bucket, that a lot of information is repeated. So you can see that the labels here with the zone and the name and the LE is unique, but the other ones are repeated for every bucket. And that leads to certain issues in atomicity that it's easy to be cut off or kind of miss some data. The other issue that we have is because we're trying to build a distributed system, that it's very easy to lead to data that is scattered in a lot of places. And having to compute a histogram function with data spread out and joining them over the network is pretty expensive for every query. So what we did is that we said, let's rearrange the data model a little bit, and let's do what I call a single histogram schema. Why not put the entire histogram into a single time series with these bucket definitions and values together? And if you do this where the histogram and the sum and the count are stored together, then we get some really nice benefits. And the same thing happens when we send raw data over, is that we are only transmitting the label values once. So first of all, that we get some nice benefits in terms of the atomicity and in terms of distribution, that we don't really have to worry about the distribution problem. The other thing is that this ends up saving a huge amount of I/O and storage. So in terms of network I/O, what we find is that for a histogram with 64 buckets, which ends up with 66 total series, we get about a 50x reduction in the network I/O than transporting separate time series separately. So that's definitely a big enough gain that the cost of switching to this format was worth it for us. The other thing we find is that we also can improve the storage costs quite significantly for histograms. So I'll go into this just a little bit. I'm happy to talk about details and collaborate on solutions for this. But for example, we can compress histograms using delta compression across buckets. And we find that when you compress it and you have a reasonable number of buckets, for this study, it is based on 64 buckets. We could get down to a very small number of bytes per bucket. It's about just below 0.2 in an actual environment. And that helps us a lot with the storage costs of storing a lot of histograms. The other thing that we found was that this actually helped querying. This was a little bit of a surprise, but maybe it shouldn't have been, is that when we switched from a schema with one time series per bucket to one with a single time series for the entire histogram, we found that the querying speed went up a huge amount. And we believe the reason for this is because, first of all, that you don't have to do group bys by the LE tag. And it turns out that group bys are not, they're not free because you have to, they're not free, right? Now, this is actually a comparison of, just to be clear, this is a comparison of our own two different implementations of how we store things. I'm not trying to compare this to Prometheus at all. That would be that's kind of beyond the scope. Now let's talk about some usability and correctness issues that this kind of histogram schema also solves. So one issue is that sometimes you'll find that with histograms where you have to come up with schemas, it's likely that your first try coming up with this might not quite be correct. You might find, I thought, I needed this level of error, or 30 buckets might be enough, but I really need 100 something, right? So, or I might need to extend the range of them a little bit. So you might find that you end up in a system with time series where the bucket definitions are not the same. And in this case, you can see that some time series have the blue buckets and some others have the orange buckets. But what happens is that if they're not lined up, I can end up with levels that are not consistent with the actual overall shape. Now there are certain corrections that you can do, and that actually Prometheus does. But the thing is that when you do a group by, because you don't have the original bucket definitions from the two different places, it is you're not able to correct for the differences in a consistent manner. So what you can do if you track the schema is that you can make a schema-aware aggregation. So you can be aware that these buckets have changed in a certain way and extend and interpolate the buckets so that the sums, basically what you want to do is you're trying to get an overall shape that is aggregated. That is what you would expect from the individual shapes. Another issue that you might have seen is one of clipping for your histogram graphs. Has anyone ever gotten anything like this? Right? So the reason why there's clipping is that happens at that 2000 is that you might have seen that. So when you have these find your own buckets, Prometheus will actually add a last bucket, which is plus infinity, to capture anything over the last bucket that you defined. The issue, though, is that if you calculate quantile, you cannot interpolate a value to infinity, right? So it's mathematically not possible to derive what is above that line, and that line is basically clipped at your last value. And one solution to that is that, well, you could just redefine your bucket. That might be a little too late, though, in some cases. So another possible solution that could be used is that you could send a max value together with your data. So that red line represents the max possible values. And the way this solves the issue is that instead of interpolating to infinity, you can say, you know what, the max value that I have is 40, so I can take the 90th percentile or rank because I have a line that I can interpolate to. So this kind of system can give you a much more accurate top-end quantile that doesn't clip. And the final feature that I think will be useful to folks is what I call ad hoc histograms. Let's say that you have a metric, and I'm going to pick one that is already in Kubernetes, the container CPU usage seconds, right? So you get this metric out of every single container or pod. And let's say that I'm interested in more than just, okay, I can get the max, I get the min, the average. That doesn't really tell me that much. Let's say that I want a rich display, like a heat map, of like what is the distribution of the CPU usage across my Kubernetes cluster. So when you have first-class histograms, you can create more than just numbers. You can create distributions out of your gauges, right? So I can create an entire distribution out of all my containers and get a very rich display of what's going on, which is really neat. And the power of this is that you don't need to know that you need a histogram. You can just run this at query time from any set of counters and gauges. And by the way, I will add that yes, it is true that you can also do this in Grafana using the building a heat map from raw time series, but just be careful of the scalability of that approach. Right. So in summary, if we treat histograms as a first-class citizen, we can help realize their potential by leveraging savings in storage and network and solving accuracies and other things like that. And it will allow us to move towards a world where some of these newer features and data structures that are coming out, such as T-digest, it will allow us to leverage that future more. So thank you very much, and please reach out for, I'm happy to talk to anyone about this and collaborate with everyone on building the future of histograms. Yep. Thank you very much. Any questions? Oh, okay. Okay, I guess we have time for one or two questions or something. If not, yeah, feel free to reach out afterwards. Oh, sorry, there's a question.
64 buckets for the histogram. I'm guessing you're talking about a production use case.
Sorry, could you repeat the question?
The 64 buckets that you're talking about for the histogram, I'm guessing you're talking about a production use case. How long did it take you to roll out the change to all the services which are using the monitoring line?
Oh, okay. The question was that when I talked about 64 histograms, he's guessing it's a production use case, and how long did it take to roll that out? I guess that's not really a question that, it wasn't a rollout, it was already there, So the data was already factored like that. Yeah. All right, well, thank you very much. I'll be around, or you can ping the Slack channel, and look forward to talking to you all. Have a very nice flight or drive back or whatever, whatever you feel. Yeah.